This is the fourth lecture in the series of lectures that constitute courses 11 and 12, classes 11 and 12, on quantum statistics and the density of states and its ramifications. The situation that we're going to talk about right now is related to an idea that we talked about in previous portions of the lecture for these two classes, which is the application of the idea of degeneracy pressure. That is, that a quantum gas lowers its energy if it expands into a larger region, which means that it applies pressure to the walls of the container that it's in. We're going to see how that idea can be applied to analyze the behavior and properties of white dwarf stars and of neutron stars. The sources for our material are the same as they have been for the past few lectures, which is Crane chapter 10, which does a pretty good job on white dwarf stars, and Townsend, which does a pretty good job, a better job, on the idea of the density of states and the ramifications of it. So this is a pretty busy slide, but it's just intended to give you the background material that you need to understand what's going on. So in astrophysics, what a white dwarf star is a system which consists predominantly of protons, perhaps some helium nuclei, and electrons in a neutral plasma. So the density of electrons and positive nucleons is such that the entire star is neutral, as we would hope it would be. And we're going to look at the effect of degeneracy pressure in that kind of system. So here's what goes on astrophysically. The first generation stars are powered by proton-proton fusion. That creates deuterons and alpha particles. The temperature is high enough that electrons are separated from the atoms, creating an electron-proton plasma. Some of the atoms might again be helium nuclei, helium nuclei plus the associated electrons, or deuterons, which are a proton and a neutron in the nucleus with charge 1, that then form a plasma with the electrons again. The whole system is neutral, so we're going to ignore electrostatic interactions. And we will claim, because this is a star, that the temperature is high enough that electrons are separated from the atomic nuclear cores, and that's what creates our plasma. The rate of proton fusion is going to decrease as protons are converted into alpha particles. And the radiation pressure that keeps them from collapse, so we're generating a lot of heat and we've got optical radiation that pushes outwards, that radiation pressure begins to decrease as the star temperature decreases and the rate of fusion decreases. Because the radiation pressure goes down, then the star begins to be pulled in by its gravitational force. And one possibility is if the star is massive enough, then the temperature increases enough that it can drive alpha particle fusion, and we'll get heavier nuclei, or it runs out of steam, of energy at that point, and just begins to decrease its radius. And we'll look at that situation. So when that rate of fusion decreases, radiation pressure decreases, and the star collapses, begins to collapse. For stars in a certain mass range, that they're light enough that the gravitational collapse is not complete and it doesn't push electrons into protons to make neutrons, which is less than about 1.4 solar masses, then the major force that ends up balancing gravitation, keeping it from collapsing, is that electron pressure due to the Pauli exclusion principle, or degeneracy pressure. And while it's still hot, it hasn't cooled off yet, it's known as a white dwarf, because when it collapses, it gets hotter. It just might not get hot enough to sustain alpha-alpha fusion. And this is where we are going to start. We're going to assume that we have a mass in the right range, and we're going to assume that we've got a hot gas of electrons and nucleons where the number of electrons is known. And we want to quantitatively analyze the balance between gravitational potential energy and quantum mechanically enforced kinetic energy to find the stable radius. So first, let's go back to honors physics 1 or physics 1 or mechanics and estimate the gravitational potential energy of a system that is of uniform density. So what we do is think about a system that has a uniform density throughout. So that's a spherical system with uniform density. And then we're going to bring in mass from the outside. And we're going to ask, how much potential energy do we gain from putting a shell of new mass on the outside of the old nucleus, of the original core, which has a certain radius and a certain number of particles in it. So now we've increased the number of particles, and those particles are attracted. So that means that the potential energy becomes more and more negative because we have decreased the energy of the particles. So for that little shell, then, the change in total potential energy of the system is the gravitational force divided by the radius, because that's the potential energy, times the mass of the system, which is the density times 4/3 pi r cubed of the original system. So that gives me my total mass. And then the mass of the shell that I'm bringing in. The density times 4 pi r squared dr. So that's a shell, right? And I'm bringing those particles in to a distance which is a radius of r from the origin of the system. So I gain that much potential energy. So that term is a gravitational term that you learned in physics 1. And so there it is, the change in kinetic energy. Just switching pens here, right? The change in kinetic energy is, adding that shell, is proportional to r to the 4th power. The total energy of the system, then, is the integral of that from 0 to the total radius, the final radius of the particle. So that might be out here, of the star. So that might be at much greater radius. So we're going to do that integral, the integral of this quantity here. And when we integrate it, we end up with this fancy set of numbers here. 16 pi squared, so about 160, divided by 15, times the density in kilograms per cubic meter of the star, the gravitational constant, and the radius of the star to the 5th power. Now again, we're making an assumption here that the mass density is uniform throughout this system, and that might not be a perfect assumption, but we're going to start with this and see what we get. So the total gravitational energy for a star of mass m, okay, is of mass m, where the mass then is equal to 4/3 pi r cubed times the density of the star, is this. So all I'm doing is making substitutions for the mass wherever I can in here. And we end up with 3 times the gravitational constant times the mass of the star squared divided by 5 times the radius of the star. So 3/5 of the potential energy if I brought two masses m to a distance of r from one another. That's actually quite a reasonable number. So the number of carbon nuclei for a star of mass capital M is this total mass divided by the mass of carbon. And then the total gravitational energy in terms of the number of carbon nuclei, right? So then we just ask how many nuclei do we have in the system, is 3/5 gravitational constant, mass of a carbon nucleus squared times the number of carbons squared as well. Same expression that we had up here. That's our gravitational potential energy, right? Where that constant B is in there. And that can be computed once we know the mass of the star. We assume that the electrons are sufficiently energetic that they are separated in the plasma from the carbon nuclei, and not so energetic that they are able to excite the nucleus into an energy state such that a neutron converts to a proton converts to a neutron with the addition of an electron. That would be called beta capture. The K edge of carbon is about 300 electron volts, so it's easy to make an ionized plasma at moderate temperatures, thousands of degrees Kelvin, right? It's easy to make that plasma without driving nuclear reactions. We're going to also assume that the electrons are not relativistic, as we did before. We'll check this, right? So the density of electrons in the system, as we had on a previous page, is related, yields the Fermi energy of the system. And so I'll plug in some numbers here and rewrite the Fermi energy in terms of the total number of electrons in the system and the radius of the system. We end up with this relationship here. All constants except for the radius, so the Fermi energy varies as 1 over the radius squared, and the total number of particles to the 2/3 power. The total degeneracy energy for the system is the energy of the electrons in the system, which is the total number of electrons times the average energy per electron in the system, with this 3/5 of the Fermi energy. And then when we plug that all together, using the fact that the number of electrons is equal to 6 times the number of carbon atoms, if it is driven through to being carbon, but it wouldn't make any difference in terms of the electron degeneracy pressure if we associated the electrons with helium nuclei, for example. But typically, the nuclear reactions for a moderate-sized star go down dramatically when the when the nuclei in the star begin to convert to carbon nuclei. So putting in all the numbers, we have the Fermi energy as related to the number of carbons and the I'm actually missing a term here. This is not the Fermi energy. This is the average number of electrons in the system. So I'm going to relabel this now and then correct it as the notes that are posted. We go here, pen. I'm going to strike this. And this is the total energy of the electrons in the system associated with the degeneracy of the system. Okay, so now we've got a quantum mechanical effect, and on the previous page we calculated the total gravitational potential energy. So now we put that all together. The total energy of the system, as I said on the previous page, it's not the Fermi energy, but the total energy of the system, or as we had been writing, it's that, okay, is equal to the set of constants over r squared that we got due to degeneracy pressure, minus the potential energy due to the attraction of the mass to the core. And now we'd like to find out what the stable radius is. So we take the derivative of the total energy with respect to the radius. We set it equal to 0 because that'll be the stable radius. And we end up with this relationship here. And this 2c over r cubed plus b over r squared add up. Then this is, remember, the derivative. When they add up to 0, then we found the stable radius. We can plug all of our numbers in, and we end up with this mess over here, which are essentially all constants, except for the number of carbon nuclei in the system, assuming that it's nucleus. So 6 times Planck constant squared divided by the mass of the electron, the Newton's gravitational constant, the mass of carbon nucleus squared, and the number of carbons in the system to the 1/3 power. Put in our numbers, and when we plug in those numbers, we get the stable radius of such a star to be about 8,000 kilometers. And that size, Earth is some 6,000 kilometers, so it's about the size of the Earth. So a star, which is originally thousands of times bigger, 400 times more radius than the Earth, reduces, what we would claim is that it reduces to a radius of 8,000 kilometers. So this is a very dense material. Once we've done that back of the envelope estimation, what's the stable radius, we need to ask about our assumptions. We assumed that the star had uniform density. We actually don't know the equation of state, so we can't calculate the density. So we're not going to check the uniform density approximation. But in likelihood, the density doesn't change very much as a function of depth within the star. We assume that the electrons are all free, and that's reasonable because the Fermi energy is, when we compute it, comes out to be quite large compared to the binding energy. In fact, the Fermi energy is so large that the Fermi velocity is going to end up being a significant fraction of the speed of light. But we assume that these are classical particles. When we go through the calculation on the previous page for a radius of 8,000 kilometers, we find that the Fermi energy for the system is about 1 million electron volts. And if we calculate the Fermi velocity using a non-relativistic relation, we end up with a number that's really close to the speed of light, maybe even greater than the speed of light. That tells us that we should actually use a relativistic approximation here for the dispersion relation, the relationship between energy and wave vector. So that non-relativistic assumption is not so good. And we can ask, how does it affect the result? Well, we can look at the effects. First, the average thermal velocity of the nuclei is still much, much less than the speed of light because they're so heavy compared to the electrons. So even at temperature, the nuclei are not going to be moving around extremely rapidly. So gravitational corrections are going to be small because we don't have extra mass due to fast-moving nuclei. There was nothing in the density of states where we assumed that it was relativistic or non-relativistic. And it turns out that the de Broglie relationship, which makes the wave vector proportional 1 over the wavelength, still holds even in relativity. But the energy-momentum relationship changes. And because of that, the Fermi energy is going to change. So making an extreme relativistic approximation, then the total number of electrons we can compute in the same way, all right, where it's proportional to the wave vector cubed, but now energy and wave vector are proportional to one another, directly proportional to one another. And so there's our density of electrons in the system, electron density rather, not density of states, is equal to numerical constants times k cubed. And if I wanted to calculate it as a function of energy, I could make a variable substitution. But we're going to focus on having calculated the Fermi velocity with the assumption that the energy of the particle is proportional to the momentum times the speed of light, or the energy of the particle, at the Fermi energy at least, is equal to h bar times the wave vector of particle times speed of light. Plug all of that in, and we end up with this relationship for the Fermi energy. And for the sun, when we put the numbers in, the Fermi energy comes out to be 1.4 times 10 to the 5th electron volts, which is much less than the mass energy of the electron. And so these particles now are traveling at a relatively slow speed as far as relativity is concerned. And we know that our correct answer sort of brackets things. Okay? And given this Fermi energy, we can recalculate what the radius would be. So we'll just keep iterating using relativistic and non-relativistic approximations. But this gives us a bracket on the Fermi energy, and it gives us a bracket on the radius. We could also ask the question, what happens if we come to a situation where the gravitational pressure is so large that it can actually cause the electrons in the system to tunnel into, spend a significant amount of time inside the nucleus, converting protons to neutrons. And when that happens, we can form what's called a neutron star. So a particle that's made up completely of N, capital N, neutrons. So there's this solar mass, or stellar mass, divided by the mass of the neutron. And the mass of the neutron is going to be 1.7 times 10 to the minus 27 kilograms. And if we take the mass of the star to be, of order 2 times the solar mass, so that a neutron star could actually form in principle, then the total gravitational energy, again, depends upon the radius of the star. And we end up with the same relationship for the gravitational potential energy and the number of neutrons in the system and mass per neutron as we had for carbon atoms, for carbon nuclei. It's got 3/5 Newton's constant, gravitational constant, times the total mass of the star squared. We can plug that in and calculate the Fermi energy, or we can plug that in and calculate the, not plug that in. At this point now, if we know the number of neutrons and the radius of the star, we could calculate the Fermi energy. So we end up with two terms, one of them being the degeneracy energy, that is the Pauli exclusion, which holds everything apart and then forces the Fermi level to be at a certain energy. And we have the gravitational attraction, same as we did for the white dwarf star. We set the derivative of the total energy with respect to the radius of the star equal to 0, with those constants that depend upon having neutrons as the limiting mass in the Pauli exclusion principle, degeneracy energy. And then we can calculate the radius. And we calculate the radius for a star of about mass 2 solar masses, and we come up with about 10 kilometers. About the distance between Albany and Troy would be the size of this object.